Then another important is the global stability. That means our wall is safe with like bearing capacity is safe, sliding is safe, but then as a mass, if it fails, that is the global stability. So especially if you are putting a wall on a slope, we have to be careful. Or if the foundation soils are weak, below there is a layer of very soft clay, we have to be careful because it can come like this, fail like this. Or we have tired walls. So here global stability is, because individually it is safe, but as a whole it may fail. So this is typically done using slope stability analysis. That means we can take this design into a slope stability program, then run this slip circles and analyze, get the factor of safety. See now, suppose like we have checked for sliding, bearing capacity, global, etc. Suppose we find the factor of safety is not enough, then we may have to go for ground improvement. And like sliding, bearing capacity, global stability, then liquefaction, especially if it's like if it is a saturated sand in a high seismic area, then liquefaction, like if the foundation soil liquefies, our wall is going to fail like that. Then even settlement, sometimes either to reduce or accelerate the settlement, ground improvement will be required. And we have a lot of options like like if the soft soil is very like 1 or 2 meters, maybe the cheapest solution is to remove that soil, replace with good quality fill. We can go with basal reinforcement, basal mattress, the PVDs. That means if settlement is the problem, we can accelerate settlement with PVD, sand piles, stone columns, like a lot of options are there. Then we have to select a most appropriate technique. Then next comes internal stability. Now again we come back to the cantilever wall. See, external stability we have analyzed, sliding, overturning, bearing capacity, then we get the length of the base slab actually. Then we do the internal, that means we analyze the bending moment and shear force on the stem and the base slab. From that only we design, okay, what should be the thickness of my stem or slab, what should be the reinforcement. The same concept here also, like internal, that means what is the function of the reinforcement? To keep this in equilibrium. So in that process, it has to develop tension. So we have to analyze like what should be the spacing of my reinforcement, what should be the tension, like that. So this we deal in internal stability. So there are again different collapse limit states: internal sliding, rupture and adherence. So these are actually, we look at each layer of reinforcement separately. So it is sometimes known as local stability. Then we also analyze the overall equilibrium, which is kind of like wedge stability and internal compound stability. Again, coming to the design methods. So there are, one is known as the tie-back wedge method, which is normally applicable for extensible reinforcement. And what is extensible? The BS defines like reinforcements which mobilize the design tension at strains greater than 1%. These are defined as extensible. And if the reinforcement develops the design tension at strains less than 1%, it is inextensible. So tie-back wedge method is considered applicable for extensible reinforcement. Then there is another method like coherent gravity method. It's applicable for inextensible reinforcement. So this is a more or less an empirical method. That means actually the method has evolved from measurements on actual structures, like the earth pressure distribution on actual structures. Then there is another like K-naught stiffness method. So in this method, only the strength of the reinforcement is considered, like the stiffness, but whereas this, it takes into account the stiffness of the method also. But normally it is an advanced method, but not yet come into the routine practice. Like, so I also don't know much in detail. See now, if you look at it, where is like normally like geogrids, geotextiles designed with tie-back wedge method, and some companies like even the polymeric strips and also tie-back. Then see, normally we have this picture like metallic is like polymeric is extensible and metallic is inextensible. It's not as simple as that. Like for example, the Gabion mesh, it is of metal, but it has got, because it's not a like a, because of this hexagonal structure, it elongates a lot. So we have to go with tie-back wedge method. And again, if you look at anchored earth, the reinforcement is metallic steel rod, but then it includes an anchor. So to anchor, to develop the passive resistance, we know like active earth pressure is mobilized at small moment, whereas passive earth pressure is mobilized at relatively large moments. So for the anchor to develop adequate pullout resistance, significant deformation has to occur. So normally again it implies the tie-back wedge method. Then coherent gravity, like ribbed steel strips, then probably the bar mats like done with coherent gravity. And again, sometimes like polymeric strips and straps also are designed with coherent gravity like that. So again, which method to use? Sometimes the codes like very clear, like okay, this like that, but sometimes there is some leeway also. And our if you look at our IRC code, so it says like extensible, inextensible, but then it is sense like which method to use is left to the discretion of the manufacturer like that. So then mainly our focus will be on the tie-back wedge method, but just to highlight the differences between coherent gravity versus tie-backs. See, one is what is known as the maximum tension line or the critical failure surface. That means where does the maximum tension in the reinforcement occur? In the tie-back, it's our like the Rankine failure plane. That means, I'm sorry, this should be 45 plus 5 by 2 tie-back wedge method. In the coherent gravity, the maximum tension line is like this. This is actually as per the BS code. In the FHWA, it's slightly different actually. So one difference is this, the maximum tension line. And basically this comes from the earth pressure theory, from Rankine theory, Coulomb theory like that. But whereas this is from the actual field measurements, like people have instrumented the actual walls, like measured how the maximum tension was developed. So this follows from the actual. So that's why it's like more like an empirical method. This is one difference. Second is the earth pressure distribution. Like the tie-back wedge method, it's mainly the coefficient of active earth pressure. That means it assumes throughout the structure the active state is achieved. Whereas in the coherent gravity, like at the grounds at the top, it is K0. That means earth pressure at rest, because the reinforcement is inextensible. So that means to mobilize active condition, we need some deformation, but because the reinforcement is so stiff, like it doesn't allow the soil to yield. So that means in this portion, upper part, it will be more closer to coefficient of earth pressure at rest. And at a depth of 6 meters, it becomes Ka. And third difference is the adherence factor or the pullout or the interface. In the tie-back wedge method, it is uniform. That means it will be some factor into the tangent to the friction angle, tan phi, alpha tan phi. Whereas in the case of coherent gravity method, this also is more. At the ground surface, if you look at the this, it's 1.2. That means the coefficient of friction could be 1.2 or 1.5, very high. Mainly this comes from the dilatancy effects. Like, see, normally what happens, like we have studied in soil mechanics, like if you have a dense sand, if you shear it, what happens? It dilates actually. So here also, like the dilatancy is there. So that is why it gives as if it gives a higher friction angle. And again we know as the normal stress increases, the tendency to dilate is suppressed. So you put enough confining stress, dilatancy is not there. So that is why at the height depth of 6 meters, it becomes like. So these are the three fundamental difference between tie-back and coherent gravity. Now coming to the internal failure mechanisms, one is internal sliding. So in if it is a gravity wall, a plain concrete wall, sliding is possible only at the base actually. but whereas this is now made of soil. So in principle, it can slide anywhere at any level. So this we check at, see normally at each reinforcement level, we'll have to check for internal sliding. So that means we analyze what is the vertical force, the horizontal force at that level, then available resistance, and it should not slide. So again, if the factor safety is less, again we'll have to increase the reinforcement length. Then how do we do the check of internal sliding? So simple, like again, it's like a friction only. What is the normal force? What is the friction? So here we have interface friction. That means soil is sliding with respect to the reinforcement. So the coefficient of friction is basically a interface friction. And this is related to the angle of internal friction of the soil. That means the coefficient of interface friction is equal to CDS into tan phi, where CDS is called the coefficient of interaction in direct sliding. Same way, like we have a pile, how do we calculate the friction? Some factor into the phi of the soil. Same concept here. So this we have shear box test actually. So see, normally to determine the angle of friction of soil, we do the shear box test. So here the difference is we put the reinforcement at the interface actually. So we have, this is fixed, this is fixed, this is moving. So there is relative movement between the reinforcement and the soil. From that we can get the interface friction angle. So we have this test actually apparatus. So we put the reinforcement at the interface, and this is fixed, this moves actually. So there is sliding at along the interface, and from that we can get the interface friction angle. So once we get that, that is related to the phi of the soil, then we get the CDS value. So normally what happens, the manufacturer does this test for different types of, sand, silty sand, gravel, like that, for different types of soil for the CDS value. Then when we are doing the design, we'll have to pick up, okay, at the site, what is the fill? So which soil which is closest to the value given, from that we can pick up the value. Or sometimes otherwise we can get the actual test conducted also. Then the second internal failure mechanism is rupture of the reinforcement. See, the reinforcement mobilizes tension, and if the tensile strength is not adequate, it will rupture. So here, so we have to ensure that the available tensile strength is more than the tension developed, the adequate factor of safety. So how do we calculate the tension? It's a very simple formula, like at any depth, like we calculate what is the vertical stress here. See now, what is the horizontal stress? Coefficient of earth pressure. Like now we are in the tie-back wedge method. So the earth pressure coefficient is Ka, active earth pressure. So Ka into sigma V will give me the horizontal stress at this level. Then we assume like this reinforcement resists the horizontal stress in this area. Like we take the midway point between these two layers. Similarly, midway point between these two layers, this becomes the tributary area, which we call SV. So Ka into sigma V into SV. It's a very simple calculation. So this will give me the tension. Like see now the calculation of vertical stress, again different codes have slight difference. So if you look at FHWA, AASHTO, NCMA, the vertical stress we just add up like gamma into H plus surcharge. If I look at this, like if I multiply the unit weight by the height plus any surcharge over that, that is my vertical stress. But if you look at BS and French code, they take a slightly different approach. Like I look at I add up the vertical forces, again the surcharge, then I look at the horizontal force, I'll calculate the eccentricity. So RV by L minus 2A. This becomes my vertical stress. So obviously this is going to give me more vertical stress and more tension. So difference could be something like 20%, 25% more. So that is why the BS will predict more reinforcement tensions. if you design with FHW, it will be more economical like that. So it is the difference between codes, like, so we cannot say the other thing is wrong or this is more right like that. Different countries, different experience, different approach, that's all. Then the tension, as I mentioned, it will vary along the length actually. So maximum is here. Then as we go to the facing, like it reduces, we don't know exactly how much like that. Like people have tried to measure, it depends on various factors, like what is the stiffness of my ribbon, quality of fill, rigidity of the facing, rigidity of the connection, depends on many factors. But schematically, this is the variation like that. And again, the tension, the earth pressure, like we have a triangular distribution, active earth pressure. So if you calculate the reinforcement tensions also, like assuming the spacing is uniform, as we go down, the tension will be more. And again, I mentioned what should be the spacing actually. So again, the FHWA, like they put a limit, like the vertical spacing should not be more than 0.8 meter. They put a limit actually. Whereas the BS doesn't really like keep quiet on that. Like, so the reason is that, so theoretically I can put just 2 layers, like 2 very strong layers also. The stability will be satisfied, but then it will not be a composite mass. Actually, we want it to be a composite mass. For that limit has been put. Okay, as long as the spacing is within 0.8 meter, it behaves as a composite mass like that. See, now I have calculated my tension, and the design criteria is the design strength, tension should be less than the design strength divided by the factor safety. Here it is the long-term design strength. See, what is the long-term design strength? This is the ultimate tensile strength. This is which we get from a tensile test, that we put the reinforcement into a tensile testing machine, you pull it, the load at which it ruptures or the maximum load, that is the tensile strength. So that has to be divided by different reduction factors. Like one is for creep, then for insulation damage, then for durability, for weathering. Then this is factor safety for extrapolation of test data. That means basically all this comes from test, and there is an uncertainty associated with that. Like if you are very confident, then it can be very low, even it can be even 1. But if your testing is not as reliable, then we'll have to take a larger factor. See, now creep, like we know, like again we are talking about geosynthetics, which are viscoelastic materials. That means if we apply a tension, we find immediately there is an immediate strain. Then with time, that strain continues like that. Like if it was steel, there is an immediate elastic. After that, no further strain. Like, but in the case of polymers, there is always a time-dependent deformation, which is the creep, and this varies as the load increases. That means as a proportion to the ultimate tensile strength. If I suppose if the applied load is only say 10 or 20% of the ultimate tensile strength, the creep will be less actually. As I keep on increasing the load, the creep will be more. Then like normally there is primary, secondary, tertiary. When the load is above a certain limit, you will find after some times the creep increases, then it ruptures like that. This is called creep rupture. So I have to ensure that, like see, normally I build my structure and it has got a life, like maybe 50 years, 75 years, 100 years. So I have to ensure that during the design life, this type of creep rupture will not take place. So for that, we do the creep rupture test. So here in the vertical axis, we have rupture strength as a percentage of the ultimate tensile strength. And here the logarithmic time, that means time to failure. So here suppose in a normal tensile test, imagine I have a sample, its strength is say 100 kilonewton. So I just hang the sample, I put 100 kilonewton, what will happen? It will immediately break. Now if I put 90% of the tensile strength, like suppose I put a 90 kilonewton load it will break after some time. So if I put 80, the time to failure increases like that. So this creep rupture curve shows that, like, as a it compares the applied load as a percentage of the ultimate tensile strength to time to failure. So basically, what is my design life? Like, if it is 10 raised to 6 is something like 114 years. We know, like, the bridge's design life is 100 to 120 years. So if I look at this, this is about 70%. What it says is, if my applied load is less than 70% of the tensile strength, then creep rupture will not occur within 114 years. So 100 divided by 70, it becomes my creep reduction factor. That means if my strength is 100 kilonewton per meter, as long as the applied load is less than 70 kilonewton per meter, then creep rupture will not take place. And again, there are tests actually, like, again, conventional creep test, what we do, like, we have the samples, we hang the weight or load, then wait. But of course, nobody can wait for 100 years like that. So there are accelerated tests, like there are, like, we know the creep is increased if I increase the temperature. So the effect of time can be simulated by testing at a higher temperature. And again, there are, if you look at this curve, like, see this SIM actually. SIM is actually an accelerated test. It's called stepped isothermal method. That means we are testing at higher temperatures. So it goes up to here, like, see, 10 raised to 6, even more. Like, also we can see conventional rupture. The pink squares like that. These are all conventional. That means actually we are applied the load at normal temperature and it has ruptured. So we can see up to here, like here we can see this is 10 raised to 4 means 10,000 hours. So normally says, like, I can do SIM test, but how do I know it's reliable? So for that actually we do the conventional, like, so these are all conventional. This is conventional run out actually. So it has done, but it has not failed actually. So when we plot the data, both like conventional test as well as SIM test fall along the same trend line, so that means our extrapolation is valid. So that is code specified. So minimum number of conventional test, minimum up to 10,000 hours has to be done. So all this, like conventional as well as SIM, it follows along the same line. So that means our extrapolation is valid. Like, so basically the manufacturer does this test. They'll give a report actually, creep rupture report. In that they'll specify, okay, for my product, these are the creep reduction factors. We can use that in design.